Chapter 20 is on nuclear chemistry, which you really can't learn in a single chapter, which means that this is just going to be an introduction to the coolest parts of nuclear chemistry. And in the first section, we are going to mostly just learn how to balance nuclear reactions, but we are going to do some definitions, starting with radioactivity. You've probably heard of radioactivity, or this thing is radioactive. What exactly does that mean? A substance that exhibits radioactivity is something that is undergoing spontaneous, so you know what that means, without any kind of help from the external environment, spontaneous emission of subatomic particles. And you also know what subatomic particles are, the particles that make up atoms, protons, neutrons, electrons, and we're going to look at some other subatomic particles as well. Spontaneous emission of subatomic particles, and a lot of times that comes along with the spontaneous emission of energy, or sometimes radioactivity is just the spontaneous emission of energy. In this process, one of the products of this is another atom. So this produces a smaller atom, as the original atom is undergoing spontaneous emission of particles. It doesn't completely decompose, it just loses some of its particles, leaving it a smaller atom with fewer protons, or fewer electrons, or fewer neutrons. We also have, opposite of radioactivity, we have a process called nuclear transmutation. And so this is like a combination reaction. This is when we would combine an atom. We'll just say a nucleus, because that's where the reaction is really taking place. Combining a nucleus with additional subatomic particles, like more protons or more neutrons or both. And this is done to produce a larger atom. So a lot of the big atoms that we have on our periodic table, the ones that have cool names, the ones that are down in the bottom of our periodic table, where, if you're looking at an older periodic table, it's not all the way filled out. Those atoms are made synthetically in a lab by people, and they're being formed through nuclear transmutation, of taking two smaller atoms and slamming them together and combining them to make a larger atom. So getting ready to balance these nuclear reactions, what I want to do is review with you subatomic particles, plus also introduce a couple new ones as well. And the ones that you are already familiar with, the proton, the neutron, and the electron, we're going to look at how they are written in a nuclear reaction. And then we're also going to learn about the positron and something called an alpha particle. So before we get into this, I want to remind you of something that we learned, like you learned a way long time ago, way back in the fall in 161, when you were first learning about how we write the symbols of elements. And you learned if we were going to be really fancy about an atomic symbol, we could write it something like the way I'm writing these ones right here. And you know that the letter is representing the symbol of the atom. That these numbers that we have in the corners are giving us some information about the subatomic particles in the atom. So down here in these spots, and this was the number that I said was useless and redundant. This is the number of protons in the atom. And the reason in 161 The reason that I said that it was a useless and redundant number was because the atomic symbol, like N for nitrogen or C for carbon, is based on the number of protons. So if you say nitrogen, you mean 7 protons. And if you say 7 protons, you mean nitrogen. So it's silly to have them both. And then you also learned these numbers up here at the top. These were our mass numbers. And these numbers were the combined total of protons and neutrons. So this was the number of protons plus the number of neutrons. And you learned that this was a really handy number because the number of neutrons is variable for an atom. So it was useful to express the mass number. That was really the only way that we had for communicating how many neutrons there were. So keeping that in mind, let's write some symbols for these different subatomic particles. For the proton, you guys already know the symbol that we use for that is a lowercase p. And if we wanted to fill in the numbers on the left-hand side, the way that we would do for an atom, well, the proton has one proton. That's what it is, one proton in it. And since the proton is just a free-range proton without any neutrons, its mass number is also going to be 1. So it does seem kind of funny to write 1 and 1 for the proton, but when we start balancing equations, this is going to make sense to you. And again, this right here, this one up here, is telling us the number of protons plus the number of neutrons in a single proton. Yes, that is actually what it's saying. And this one down here is telling us the number of protons in a proton. It really is that goofy. We also can write the symbol for the proton as an H for the hydrogen atom. That's another way that you might see it symbolized. The neutron, as you know, we symbolize that with a lowercase n. How many protons are in a free-range neutron? There are none. And how many protons plus neutrons would there be? There's 1, so there's the symbol for a neutron. The electron, we're symbolizing with a lowercase e. Let's start with the mass number first. For a free-range electron, proton plus neutron, there are no protons, there are no neutrons, so the mass number is 0. For the other number, the number of protons in an electron, you might be thinking it's 0. That does make sense. That's exactly what we did with the neutron. However, because protons and electrons are oppositely charged, the electron essentially cancels a proton when we're thinking in terms of charge. So we put a -1 down in the bottom for that. We also occasionally will write the symbol for the electron using the Greek letter beta. Sometimes electrons are called beta particles. In fact, when we're in nuclear chemistry, it's more common for them to be called a beta particle than for them to be called an electron. The positron is the opposite of an electron in a true sense of the word, not the way the proton is. So the positron has the same mass as an electron, but it has an opposite charge. So for the positron, in order to really communicate the difference between a positron and a proton, we use the symbol E, just like we would do for an electron. And instead of writing just a regular 1 in the bottom corner, we write +1. And again, why are we using this goofy notation? That's just history. That's just how it's done. We can also write a positron using the beta symbol. Again, +1, which is distinguishing it from a proton. It is same mass as an electron, but oppositely charged from an electron. And then last but not least, the alpha particle, which is given the symbol, the Greek letter alpha. Alpha particles have 2 protons and they have 2 neutrons. So 2 protons plus 2 neutrons gives it a mass number of 4. And the alpha particle is actually a helium atom. So you could also see it written like that. So what we're getting ready to do right now is learn how to balance nuclear reactions. When we're writing a balanced equation for a nuclear reaction, we balance them not in terms of atoms like we normally would, but we balance them in terms of subatomic particles. So they are still mass balanced, but they're not going to be atom balanced. And this feels really funny at first, feels really weird at first, but you'll get the hang of it really fast. So here's an example. This is radon with a mass number of 222. And when we're writing nuclear reactions, it's really common for us to show all of these numbers because it helps us balance the equations easier. And the product of this radioactive decay is going to be polonium-218. That has an atomic number of 84 and an alpha particle. And so when we're looking at these nuclear reactions, you can see clearly it's not balanced by atoms because we have totally different atoms on the left-hand side and the right-hand side. But what we're doing here is balancing it by particles. So in terms of protons, we have 86 protons on the left, and we have 84 plus 2 protons on the right. And then in terms of mass number, we have 222 on the left and 218 plus 4 on the right.